Okay, good afternoon and welcome to this dark, rainy afternoon. This is a pretty much generic presentation for the undergraduate and postgraduate students in chemistry on risk assessment. Although principally it's written for CM3292, which means the examples I use are from that module, it is generally applicable. Before I proceed, I need to acknowledge the advice of the Office of Safety, Health and Environment, and also particularly the sterling efforts of Stephen Sinyin Chui of the department. I have, I'm afraid, plundered and plagiarised their slides through this to produce this somewhat truncated presentation on risk assessments. Okay, so let's proceed. When we think about risk assessments, we need to apply both common sense and your specialist chemical knowledge. So let's first of all just define what we mean by risk assessment. Okay, here's a couple of definitions. I won't read them to you. I'll let you read them. Effectively, to start the systematic process we call risk assessment, you need to sit down and think about what might cause harm to people or property within what you are doing, and decide whether you are taking reasonable steps to prevent that harm. So in one sense, it's fairly straightforward. Let's continue thinking about what risk assessment is and actually what it isn't. These always seem good quotes to me. How can one study chemistry at university without thinking about Hamlet? There is a special providence in the fall of a sparrow, cause and effect. Or even, dare we say, King Solomon. The race is not to the swift, nor the battle to the strong, but time and chance happeneth to them all. Sorry, authorized version. Randomness. Risk assessment actually addresses cause and effect. It does not address randomness. That should guide our thinking about what things we consider present hazards and then potentially risks. Risk assessment is not about creating huge amounts of paperwork. It is simply identifying real risks and sensible measures to control those risks. With risk assessment, we cannot ever guarantee to completely eliminate hazards or risks. We minimize them and control them, and then make a decision as to whether the remaining risk is acceptable or not. Okay, let's now have a look around briefly. Why risk assessment? Well, there's a couple of incidents that have occurred around the world. There are sadly many more. Not only to very young people, but to people who are, one would think, much more experienced. And if we want to think about closer to home, yep, here's a couple of examples that have happened in our university and in some cases in our department. Let's, for interest, let's look at one that did happen in our department, or rather simply the report from that event. It makes interesting reading. Somebody was carrying a round bottom flask on one of our modules. They tripped, fell and cut their finger. So this is the report of that incident. It's instructive to look at this and think about how could that have been minimized or prevented. not necessarily straightforward. It was simply a trip and fall. So some types of accidents you can reduce the possibility of, so you make sure you haven't got, in this case, boxes and things in the way of walkways. But sometimes things, randomness, will happen. Okay, let's proceed. Objectives of risk assessment. Well, it's obvious in one sense, and I won't read these. I'll just let you read them. The important things here is when we've gone through the process, we can assess whether the task, the experiment, the procedure is actually safe enough to proceed. It will never be risk-free. And whether the existing controls are sufficient. Maybe one of the things we don't think about as directly is whether it complies with the legal framework of where we are working. And in Singapore, there are a number of major frameworks, but for instance, the Workplace Safety and Health WSH Act. We do this for clearly obvious reasons, but additionally, it's part of your professional skill base as a chemist. If you can't work safely, you'll probably kill yourself or kill others anyway, he said grimly. But actually, you shouldn't be working as a chemist if you cannot design and execute safe experiments. Right. Okay, let's think about what those types of regulation are in Singapore. There are 3 key principles to the WSH. Reduce the risk at source by requiring all stakeholders to eliminate or minimise the risks created. That is risk assessment. Now understand this is a legal requirement. The language is slightly different to maybe the language we might use, but bear in mind afterwards, when you end up in court, these are the types of phraseologies that we're talking about. Require industries, and in that sense, the prime mover at university is you, to take greater ownership of safety outcomes, impose heavy penalties for poor safety management. Those penalties are both institutional and personal. They can be very expensive penalties or career-breaking penalties. If we look around the world, there are incidences where, for instance, chemists have been imprisoned. This is serious stuff. Risk assessment regulations are the second thing that we need to think about here. They require the principal, you and me on 3292, and the department and the university, to conduct risk assessments in relation to safety health hazards at the workplace. That means risk management and risk assessment are really important in our laboratories, the things we do in the lab. Okay, that's the introduction. I'm going to close the introduction part of this. You can look at these later with various sources of further information. I would suggest some of these are very significant tomes or documents. I am not expecting you to read this sort of stuff for this module, but I'm simply highlighting the existence of this material. Of course, you have on 3292 specific workshops on risk management in week 1 and risk assessment, and that I hope will help you more clearly define what your role and what you need to do in this module. Okay, let's move to the actual process. So, who conducts and approves risk assessments? Well, you conduct the risk assessment because you are doing the work. And I would also suggest that this is not an individual thing. You're working in pairs. In this module, we're suggesting you work as a team. The pair of you, many heads, will produce a better and more robust result. Remember though, you are trying to assess real risks, not groundless fears. We'll talk about that more later. So you do the assessment. It's approved by academic staff. Technical and lab staff can advise you. They will not do it for you. Note please that GTAs do not approve risk assessments on this module. What sort of information do you need? Well, some or all of these, not all of these. Location, facilities where you're doing the work, the practical script, you need that. List of operations, that's something that you'll devise in the workshop as you do your risk assessment. List of chemicals and their hazards. Usually we would use the MSDS, the materials data sheets. You will need access to these. Crucially, the context under which you are using these chemicals. And finally, relevant codes and practices, probably less important for what you are doing on 3292. So the first step in doing a risk assessment sounds very obvious and stupid, but to identify the risks. Now, there are hazards, there are uncertainties, and there are risks. If you identify something, whatever, that if it happened would harm people or property, it is defined as a hazard. Now, according to its likelihood, a hazard is either an uncertainty or a risk. So if you're not sure it will happen, but you can estimate the odds, it's pretty much a risk. If you don't even know the odds, it's an uncertainty. So, you identify hazards from your protocol, what you're doing, and the MSDS. You evaluate the risks of a step You evaluate the risks of steps in what you're doing, and hence their consequences in terms of their likelihood and severity. We'll look at that in a moment. And then when you've done that, you suggest ways to control the risks associated with those steps. And you would use the hierarchy of control to do that. Okay, let's continue at the moment before we get to actually doing this. What the hazards identification process might look like. So, hazards can be either based in what you are doing, procedures, for instance, going out and taking soil samples, or a step in a protocol that you're using in the lab. They can be substance-based, the chemicals you're using, or they can be equipment-based, the equipment you're using. And this is a good way to think about identifying risk. If we think about 3292, what typical risks might there be? Sample preparation, preparing your samples for soils you're using aqua regia, for instance, not the most friendly type of substance. You could be using needles in various of the practicals. You're going outdoors, so there's safety. It's field trips here, but actually you're not doing field trips, you're just doing sampling trips. The use of general and volumetric equipment. It sounds silly. A simple pipette is it can be a very dangerous piece of kit if you don't know how to use it properly. As a first aider, I won't talk about it here, but maybe in the lab I'll show you one of the really quite serious accidents that can happen just by misusing volumetric glassware. using analytical instruments, for instance, distillation of liquids. So all of these types of hazards and potential risks are plumbed in to 3292. That's not a complete list. There are clearly many others, but they're the types of category and some examples. Quick slurp of tea. Okay, so how do we identify hazards? Well, we break down the experiment. An experiment starts with the input, the stuff you're starting with. For instance, the equipment, whatever chemicals you might be using, the sample collection, transportation, maybe the storage, and the personnel. The input, the things that go into whatever you're doing. Next, there's the laboratory or workshop or the activities or the operations. What you do to these things you've input. Extraction, isolation, purification, some chemical reaction, whatever. And finally there's the output. Well, you have waste to be treated or disposed of or stored. There's the handling of it, and there's your actual sample or the thing you've produced. But most of the output is going to be waste. And just to give you a prod, I suppose, many of these are relevant to 3292 and other processes, but here, some of them particularly are highlighted that would appear in probably most of your risk assessments. Now, you've got a dilemma with risk assessment. If you make the tasks too general, the related hazards and risks might be missed, which means your risk assessment is ineffective. If you go totally OTT, if you identify too many risks, which are irrelevant, probably groundless fears, your risk assessment becomes impractical, ineffective, and actually dangerous. One of the potential hazards of risk assessment, which is so massive that it becomes useless, are that students don't get to understand what is really hazardous and what is not. And we'll talk about that a bit later, because then it's dangerous, because those students are unable to differentiate between the two and basically have a inbuilt cynicism that everything is dangerous and they can ignore the risk assessment. Just as much a problem as not doing the risk assessment in the first place. Okay, probably the next stage is to look at the form that you'll be using, and this is typically, it is actually the risk assessment form that we use in this department for our practicals and for our research work actually. Okay, so depending on what you're doing, in parts of 3292 or in 3291, you'll download this template. In 3292, actually this risk assessment, or an outline risk assessment, will be actually attached to your practical scripts. And your mission, in certainly the analytical practicals of 3292, will be to tighten this risk assessment up. This is on one page. It may be that your risk assessment goes on to more than one page. If you're producing in 3292 risk assessments of n pages where n is greater than 2, it may well be that you are on the wrong side of that dilemma. You are being too detailed. It depends. That's just a general guide. When you're in the lab doing it, clearly you'll be talking to staff as you proceed. Now, what we're going to do for the rest of this presentation, which won't go on much longer, you'll be glad to hear, is we're going to fill in parts of this form. So we'll be thinking back to the form, and we'll start here by identifying the possible hazards. So we've got 3 headings here, which is where we'll start, and let's do that now. So here we go. We've started assessing our hazards, first stage of our risk assessment, and this is not something in 3292. In fact, it's something in 3291, but it really doesn't matter. Pardon me. If we go back, each step has a number, and then the description and the hazard. So we'll do that now. The step, the first bit of broken down, is to add 1 ml of diethyl ether to wash a product on a Buchner funnel flask and let it air dry for 5 minutes. Sometimes one step has more than one hazard or more than one risk. So there's chemical hazards of diethyl ether. There are fire hazards. Diethyl ether happens to be explosive or form explosive mixtures in air. It's very flammable. And the human factor. Inhalation due to transfer. Diethyl ether is an anaesthetic. You can't necessarily predict human factors very well. Maybe somebody's not slept the night before and they're very tired. That's a human risk factor. Difficult to capture them in a risk assessment, but nonetheless they exist. In terms of possible accidents, an outline of what those hazards might yield in terms of accidents. Note, not all possible accidents under every possible human and environmental situation. So an aircraft crashes into the building, which makes you throw something onto the floor and cause an explosion with the burning fuel of the aircraft. Not all possible situations, just likely situations. Anyway, we'll get to that more in a moment. Okay, so the second part of the form, we've got the possible accidents and we've taken one of them here, and the first stage is to say, well, what are the typical risk control strategies or the mitigation that the operator will be using? Now, you can assume, if you are working in an NUS laboratory, in fact I hope any laboratory, that you will be wearing standard personal protective equipment, standard PPE. In this department, that's defined as a laboratory coat and safety goggles. Now it may be that your operation requires more than standard PPE. You may require gloves. If you want chemical resistant gloves, you'll use nitrile gloves. If you just want much lighter protection, you might use surgical gloves. Make sure you know the difference. So you might have standard PPE plus gloves, which you'll have defined what type they are, and you might decide you're going to work in a fume hood for these types of chemical accidents or hazards from your material. If it all goes horribly wrong under these conditions in a fume hood with that, how severe could it be? Well, you're properly protected, you're in a fume hood, the severity is likely to be quite low. And in the next couple of slides, we'll define the severity likelihood scales. How likely is it? If you're doing it properly, probably very unlikely. And 1 is the minimum in these scales. The risk is the product of severity and likelihood, so 1 times 1 is 1. In those conditions, that would be considered that you had mitigated the risks accordingly. If you weren't doing this, you're doing it on the open bench with Bunsen burners, no PPE, then these numbers would be rather different, and that would give you an unacceptable risk quotient, a product which would then mean you'd need to mitigate further. In this case, that's 1 is fine. If it's 3 or higher, you would look more carefully and you'd have additional risk control, and we'll look at that in a moment, and you define the person responsible and the date. Let's now look a little bit about the detail of what these numbers mean. So here, for severity, we have a score of 1, which is low severity, and there's a sort of definition there. 2 is medium severity, definition there. 3 is high severity, definition there. And we're not talking toffees and chocolates here. High is fatal, serious injury or life-threatening. Medium is still injury requiring medical treatment or ill health leading to disability. This is not trivial. Just to give it some context, the score, especially if it's 2 or 3, will lead to you thinking about mitigation, and these scores will usually not change unless you're changing the equipment or the process, typically the mitigation process. Okay, so that's the severity. The next column was likelihood or probability. Let's look at that. And again, 1, 2 or 3, unlikely, a remote possibility, hasn't occurred in the PI's lab or previously. Possible, has been known to occur in either the PI's lab or some similar lab. And for the PI's lab here, you can read the teaching lab. Or likely, frequent, 3, it often occurs. So you consider realistic aspects, past experience, the complexity of the activity, the number of people involved in the activity. You can read this here. I won't go through it now. But the key is, if it's never occurred before, it's going to be pretty much unlikely. If, on the other hand, it happened last week in a lab at another university which is doing a similar thing, and it happens often, you would need to consider it likely. And usually, if it's likely, you're probably looking at extra mitigation. Or at least your mitigation needs to be such that it does genuinely mitigate. Okay, now we have likelihood multiplied by the seriousness, if you like, to give you the risk level. So consequence, likelihood gives you risk, and this matrix is important. You'll use this matrix, maybe not with quite those 2 axes, in a number of risk assessment activities you might do professionally. If it's extremely unlikely and it's the severity is extremely low, clearly the risk is going to be extremely low. If it's very, very likely and the consequences are huge, then the severity is going to be very high. And therefore, anything in this area, pretty much we won't allow it in our labs. So you're going to have to mitigate using different equipment or different processes or different chemicals. If it's in the mid-range, again, we would suggest you try to mitigate. 3 can be acceptable. 4, mostly it's probably not acceptable. Exceptionally it can be, but would look very hard at that. If it's 1 or 2, pretty much we would consider that mitigated appropriately. And again, that's really a summary of what I've just said. Low, medium, high risk. Certainly anything above 4 is not acceptable in our teaching labs, pretty much not acceptable in our research labs. Usually we would look very, very hard for further mitigation. So, coming back to the form, we would then fill our scores in here, and we'd have a risk level of 4 for this particular process. We would then think about additional risk control. Might be passing various training programs, follow the protocol, reduce the quantities or concentration of reagents, install a shield in the fume hood, replace one reagent which is rather hazardous with one which is less hazardous, etc. Which leads us into the final part of the presentation. How to control risks, and we're going to look at additional risk controls, administrative risk controls, engineering risk controls, and substitution. What do I mean by those things? Well, there is a so-called risk hierarchy, and we'll have an amusing little crocodile thing in a moment to explain these maybe in a bit more detail or describe them for you in a slightly different way. The most preferred way of reducing risk is to eliminate it entirely. Physically remove the hazard. What would that mean? Well, it might be deciding the process is physically too hazardous and you're actually going to do it another way, do something completely different. We won't have that experiment. That's eliminating the risk. It could be that you want to substitute something which is rather hazardous. So maybe you have an experimental protocol which uses benzene, which is carcinogenic, and various other hazards, and you could replace it, change the reaction slightly to replace it with toluene, which is much less hazardous. So by doing that, you change what you're doing, you've substituted something, and you've made the process less hazardous. You could have engineering controls. So basically you isolate people from the hazard. So the hazard is happening in a fume cupboard. Maybe you have shields and barriers so that even if the worst happens, which you're expecting it not to do, but the person is separated from the hazard. Or you may have technological safety alarms or mechanized things which prevent the person getting near to what you put your hand in, it shuts something down, that type of situation. Administrative controls. You change the way people work. Maybe only certain types of people, maybe only the academics are allowed to do it, or specially trained technicians. You have signage, auditing, stuff like that. Now, those sorts of things happen routinely in the department and in the university, but you're coming down least preferred. Up here are the most preferred ways of eliminating risk. When you have to start changing the way people behave, that's more complicated. And even with engineering controls, people are inventive, they will find ways around them. Finally, the least preferred method of risk control is protecting yourself, PPE. So hopefully we're only doing that as a last resort, as a last line of defense. If it goes bang, the person that is doing the work has some protection. So hopefully, I hope this gives you perspective. Let's look at these hierarchy of controls again in a slightly more humorous way. So we start first with the identifying the risk. We appear to have a large crocodile. The second stage is evaluating the risk. So again, we're summarizing the steps of risk assessment. Yes, it's possibly not a minor risk. Then what do we do with it? Eliminating it. I do think the crocodile looks quite sweet there. We kill the risk, we get rid of it entirely. Or maybe we think a crocodile is too great a risk, we substitute it with a cat. Fine enough, you've substituted the risk, so you've got a less risky proposition now than what you had. We'll continue. Isolate the risk. That will be an engineering control. But you can see intellectually the issues. The crocodile might escape if your engineering control doesn't actually predict human nature, what human beings might do. You can educate and notify people about the risk. Yes, enter at your risk. Vicious dog, oh no, in this case, vicious crocodile. You can wear personal protective equipment, and this describes nicely why this is lowest in the hierarchy, the least preferred control. Or you can run away. You can escape from the risk, even less preferred. Okay, you'll be glad to know we're nearly at the end. So here's a risk assessment flowchart, which I'll leave you to look at. Finally, what do we do if so what happens if risk assessment is done excessively? Not everything is hazardous. Please use your common sense. And here is an example here about drinking tap water. Even water in excess is toxic, and maybe the water contains impurities. And I hope you view this as humorous, and I hope none of you think of this in a very serious way, because it's designed to be humorous. As a chemist, part of your graduating skills and your professional skills are you can differentiate between hazards, real risks, and fears and uncertainties. Okay, final slide. Our environment is full of these hazards and risks. Some are real, some are unreasonable fear. Risk assessment differentiates between them and reduces uncertainties. A risk assessment should identify the hazards in any activity, suggest control steps, and those risks are considered in the light of their likelihood and severity and context. To give you a silly example, the risks and, for instance, the PPE you might have to use if you are manipulating 1 microliter of concentrated nitric acid are very different from if you were manipulating 5 litres of concentrated nitric acid. So you cannot get your PPE directly from your MSDS, because the MSDS for nitric acid will say the same thing for 1 microliter as it would say for 5 litres. So it depends on your context. And finally, a nice little flow diagram about life, the hazards and risks and fears and uncertainties it contains, what risk assessment does, and what the result of risk assessment with mitigation is. Okay, I've said quite enough, I think. So thank you very much for listening. It's stopped raining, so I need to go and get a rain sample. Thanks a lot, guys. Take care and work safely. Bye-bye.